Alrighty, this week we're going to work on completing the thermochemistry chapter. Last week we learned how to use Q equals ms delta T to solve a whole bunch of different word problems. Today we're going to focus on manipulating and adding reactions to come up with this same delta H value. We're also going to use stoichiometry to do that. The stoichiometry one will look super familiar. We're just introducing a new conversion factor using the heat of the reaction. Enthalpy of formation values will be discussed, as well as using bond breaking and bond forming energy values to calculate delta H of the reaction. So we already got this one done right here. And the rest of our focus this week will be completing and learning how to use these four approaches. So before I jump into that, I just wanted to mention an overarching term. So you'll hear about Hess's law quite a bit. And I've actually seen Hess's law used to describe several of these processes. And so what's the takeaway then? What is Hess's law, and why are they saying, okay, now we're going to learn about Hess's law, like if you look in a textbook or something. So Hess's law is basically a state function. And for chemists, it's a state function used to calculate delta H. That begs the question, what is a state function? So you all need to know about state functions, regardless of where this course is taking you. A state function is any kind of calculation that's path independent. So the state function is path independent. When we have traditional lecture, I usually ask the class, well, what if there's a really, really tall building, a skyscraper, or just a super tall building? You're on vacation and you're walking around a city like New York City or San Francisco or something, and you see this super tall building. And you're like, wow, how tall is that building? And then I imagine you all can come up with a bunch of different ways to calculate the height of the building. Some people are like, let's just get a super, super long tape measure and measure it directly. Right? That would be a possibility if you had a tape measure that long. Other students have suggested, well, what if you knew the height of just one floor, and then you knew, oh, you were able to count like by the windows or something, oh, there's 50 floors in there. And then you would be able to multiply the height of one floor times 50 and get the total height of the building. Other people, and this discussion would get really fun, other people would come up with other ideas. Some people that love math and love physics would often suggest to me, well, what if you use some kind of triangle approach where you're using Pythagorean theorem? So a squared plus b squared equals c squared. I've also had people suggest, well, have someone drop an object of known mass from the top of the building, see how long it gets to take to the ground. See how long it takes to get to the ground, and then using acceleration due to gravity, you can go back and calculate the height of the building. So there's so many different ways, and I imagine you're sitting there at home thinking of even more ways. It's kind of a fun thing to puzzle about. How can I calculate the height of this building? But at the end of the day, we should all get the same answer. And that's what it means to be a state function and to be a path-independent calculation. It doesn't matter what technique we use to get our value. The value, the end value, is independent of the way we calculated it. And the same could be said for delta H. All of these different approaches should result in the same end value at the end of the day. Alrighty, let's look at number 8 on page 7 to introduce us to some of the ways that we can manipulate these reactions. So this is an introductory problem. Start developing some of the techniques. There's a reaction here, and we know the enthalpy of that reaction. The scientists were able to obtain that. Then we look at A, And we're going to start comparing these two reactions. Well, how is A different from the known? And it looks like it has the same reactants and the same products. The only difference that I'm noticing is that this is 3 and this is 1. And this is 2 and this is 6. So the coefficients are different. It looks like these coefficients are 3 times greater. So it's been multiplied by 3. So since the reaction has been multiplied by 3, the delta H value for this reaction also has to be multiplied by 3. So delta H for this particular reaction, I'll call it reaction A, equals 155 kilojoules times 3. So that equals 465 kilojoules. So if you notice the coefficients are doubled, then you multiply by 2, and so on and so forth. All right, let's compare letter B to our original. Well, what I'm noticing with this is that these are reactants, and over here they're products. Coefficients are the same. It's kind of like it's flipped, right? So if a reaction is flipped or reversed, then that means that we have to change the sign of the delta H. Basically, to kind of give you some background on it, this is positive right here, right? So that means that this is an endothermic reaction. However, when we reverse an endothermic reaction, it becomes exothermic. But the big takeaway for this type of problem is if you notice something's flipped, you're going to change the sign. The quantity is going to be the same, but we'll do negative 155 kilojoules here. In letter C, we can see how, we'll see how we can start combining these kind of manipulations. So in letter C, we have a flipped version of our original. But in addition to it being flipped, it also looks like it's divided by 2. So let me make note of both of those things. And divided by 2 or divided by half. So I'm going to take my, I'll write reaction C here. I'm going to take my original value, the 155 kilojoules. Since the reaction is flipped, I got to put a negative sign. And since it was halved, I'm going to divide that by 2. So my delta H value for reaction C equals negative, don't want to forget that negative, 77.5 kilojoules. Alrighty, let's look at number 9, where we have a chance to not only manipulate the equations, but we're going to also add them up to figure out the enthalpy of what I like to call a target reaction. So how I approach this, I look systematically through the target reaction. So for the first thing I see is phosphorus pentachloride. And I notice that this equation here has phosphorus pentachloride on the reactant side as well. So I'm going to use this as is, and I'll rewrite it here. I typically worry about the coefficients after I have all my reactants and products in place. But you'll see different people do different things, and that's okay too. So since I wrote down this equation, like just copied it exactly as is, I'm going to keep the same enthalpy value. So then comparing, now I took care of phosphorus pentachloride. Next thing I need is phosphorus trichloride. And it looks like our second equation, or this equation here, will give us phosphorus trichloride on the product side. Again, I don't need to flip it or anything. Let me just copy it down. One recommendation would be to keep the reaction arrows underneath each other for purposes of canceling and adding. And my delta H value is negative 2,439 kilojoules. So now I'm going to add these two equations up, and we can cancel from left to right. So basically you're going to cancel on the diagonal. Think of a big X. So these reactants cancel these products, and these reactants cancel these products. If there's another equation, sometimes we got 3 or 4 that we have to add up, you can still cancel along that X. So these reactants could cancel with something that was written up here if we had 3 in a row. Just you're canceling on the X. Has to be exactly the same to cancel. So for instance, I noticed that P4 will cancel. It's along that diagonal. The diatomic chlorine, well, they're both gaseous, they're both diatomic chlorines, but this one has 6 and this one has 10. So when you have different coefficients, you get rid of the one that has the smaller coefficient value. And then that means that we're getting rid of 6 moles of diatomic chlorine over here. So we're going to be left with 4 at that point. Now, we cancel everything we can cancel. So reactants stay on the reactant side, and you bring down all of your reactants that you didn't cancel out. So here I have 4 phosphorus pentachloride moles, and then 4 moles of phosphorus trichloride, and 4 moles of the diatomic chlorine. Since I just added these 2 equations, I'm going to add these 2 values. So I get 999 kilojoules. And at this point, let's see how we're doing. Our target, well, it looks very, very similar in terms of the species. The only thing I would say is, well, we have different coefficients. There's a 4 here and a 1 here. So let's just divide this whole thing by 4 so that it matches. Like 4 divided by 4 is going to give us that 1 that we know that's there. So then it matches. I'm dividing this resultant equation by 4. And that means I have to divide my enthalpy value by 4 as well. And so my final answer for this problem then is going to be 250 kilojoules. And that's the enthalpy of this target reaction.